I won't forget.
So we've only got 18 people. I was hoping.
Yeah, I was expecting
more.
even more.
Yeah. Okay, well, I guess we'll kick it off and others can catch up. Okay, so I wanted to open up today by saying welcome to any of those from the Wednesday lab section, and offer my apologies out there for the ad hoc difficulties in trying to get some plotting and visualizations that made sense work. I know it was a little difficult to follow sometimes, and that's hard when you're jumping around code and figuring out how it goes from there. But that being said, we have it all squared away today, and as always, I will be providing the polished notebook for use with your lab questions, and I hope those of you who are from the Wednesdays lab that aren't on the call right now, that you do take the time to listen to this recording. And yeah, so I think we'll kick it off from there. I'm going to do a little bit of a review catch up of where we got to last week. So we've got our starting point to kick off from, and then we're going to go through some of these really quite interesting visualizations and powerful ways to quickly get a summary of things to interpret, which is the goal here, right? We pull data in, we want to generate some sort of a visualization or statistic or summary to help us evaluate the data. Okay, did you want to talk about regressions, or do you want me to get everybody caught up from last week first, David?
Yeah, just very quickly, we'll be continuing on with that data and looking at trends. I mean, this is the big thing, you know, sea ice trends. So we'll be doing this, and the way to do that, the first order way to do that, is to just put a linear regression onto it. And it's interesting. You'll start to see, you know, some tiny cracks in use of linear regression. But we'll get to that later on. You'll start to see what I mean as actually accurately representing the nature of the trend that you're seeing in the data. So anyhow, yeah, so with no further ado, I guess we'll commence, Adam.
Great.
Yeah.
All right. Well, I should grab the screen share. Oh, David, I think you have to re-enable screen share.
Sorry, yeah, we had, and then
Dropped off, didn't it?
computer went offline. I hope it doesn't do that today.
Okay, so here we are.
Should we open the same lab where we left off last week? The same notebook, I mean, rather?
Yes, I think that's a good idea. If you were working around, playing around, kind of making a bunch of different cells and working through and doing everything last week with us, then possibly open up a new workbook, maybe label it week 2, and then as we catch up, like as we recap from last week, you could copy and paste across. So I think I'm sharing now. So kind of what I'm suggesting is, if we had just to make it kind of clear on what I'm trying to suggest, if I open a new notebook, to one side, I've got empty cells on this side, and then as you kind of see where I'm kind of pointing to and following up, you could go, okay, well, let me take my last week's and I'll just put that in there and step through that way so that you've got a fresh starting point, but you're still just using the code from last week. Great question. That's good. I do always encourage fresh starts, but also you don't want to have to retype everything. So yes, that would be my recommendation, but we will be recapping the code from last week and pulling that up so that we can continue on from there. So that being said, this is where we should be from last week. So last week we had pandas and glob as our libraries that we brought in, as you can see here. A couple of ones that we're going to be adding this week, and I'm going to break them apart a little bit. And we've seen this one here before, Numpy. Okay, so that is just as straightforward as import Numpy as NP. We have seen the next one here as well, the Plotly graph objects. We've used that before as well. This one here is new to us. We haven't loaded it in before, but it is still part of the Plotly library. So it's similar to the one prior to it. It's import plotly.express as px. So we use, instead of go, we use px. But we want to include both of those today for some of the plots that we'll be pulling in. And then just to, we're laying a bit of groundwork here. I mean, we didn't put these in last week, but we also want to pull in a couple of others for our linear regression. We don't actually need this one, but you could pull it in anyway. There's no harm. So slightly different layout in these ones. We're going to use a from sklearn, and we've got our dot linear underscore model, all lowercase, and then we're going to import linear regression with a typecase text. So a little bit of a different format. We don't have the import as, we have a from import. Okay, so for ease, because those ones are just a little bit of a different format, I'm going to toss those into the chat for you. Okay, so that should be our first cell in our new notebook if we're going to copy and paste across from what we had last week. From there, everyone last week should have gotten to this point here, where we were able to create a data frame from our 12 CI6tent files, and we used our read CSV from pandas, and we used our glob, which was something we covered last week. Once we had our data frame in, there were two other important steps that we had to make sure that we did. The first one here was we reassigned our data frame variable by setting the index to our date time column, which we created through our read CSV here using the year and month columns. The next one here was we wanted to resort our data frame. So the first row to the nth row, we wanted that to be in chronological order through time. Okay, so here we took our data frame, we used the function sort index, because now we've got our date time index assigned, and we used this argument here, in place equals true. So you will note here that the first part where we set our index, we are reassigning our variable df, whatever we've set df as. And here we're just running the function with an in place argument. All right. So I have a fresh kernel. I don't have anything loaded yet, so I'm going to execute that file. And I'm going to drop a couple of empty cells in front of it. Okay, so I executed that cell. If you've got that into 1 or 2, maybe 3 cells, that's fine. Execute those. Everybody should be able to get to the point where if you were to take a look at our data frame, you would see something like this, which was the output that we achieved last week. We have a date time index that is in chronological order. And we have 4 other columns, one of which is our extent, the numeric column we're going to be most interested in from our data set. All right. And I would also recommend that you add a cell that is df.columns right underneath this first cell that we've gotten ourselves caught up to. Now, can somebody tell me why this is going to be relevant or important with our current data set?
Because then we can see the spaces that are added in front of each column name, so we know to include them when we're trying to call up specific columns.
That's right, exactly. So we didn't do any column renaming up here in our read CSV, but we know we're bringing in CSV files. And we've learned in prior weeks that the CSV files can be a little temperamental in whether the whomever created them added a space in front or after the comma, and the pandas read CSV reads it in verbatim with columns and spaces of characters. So this allows us to get that quick visual, just like how I was saying there, about whether there's any leading or trailing spaces in our column names to try to, prevent us from having these errors thrown and having to go hunt them down. Thank you, Carl, as well, for your comment on spaces in the chat. Okay, great. So this gives us an idea. Looks like extent, the one we're interested in, has got 1 leading space. But if we were going to look at another column like area, looks like there's more than 1 space in front there. Okay, so if we wanted to use the area column, we want to be aware of that. One nice little thing about running this as well is in the output from this query, you can actually select or highlight, and Control-C and Control-V will paste it. So the nice thing about this is if you are worried you don't know how many spaces are in there, you couldn't count them, you can't quite see them, you can copy paste it, and that way you know that when you call your column in your data frame that you've got all of those missing spaces, whether there's 1 or more. All right. So now that we've got our data in, we've taken a look at some of our column names to try to compensate for some potential issues that we may run into. Let's move on to some of our plotting. So I'm going to scroll around, forgive me for a moment here, catch up to what we did last week. Nope. So then, come on. That wasn't it. Oh no. Oh, ha. That's helpful when I just remove things entirely. So you should have in your notebook from last week something that looks along the lines of this. So this was a custom function that we created ourselves last week. I will throw this into the that for a minute. Owen, yes, absolutely. Thank you. And he's back. Thank you, Owen. Yes, indents, really important here that we make sure that we do keep those indexed. So indents. Our function here ends in the colon. Everything below the colon needs to have one index in. We have additional indexes for things inside our functions we've been familiar with before. But it is really important that after the colon, inside our function, we have one indent for all of the things that are included inside that function. Thank you. All right, so everybody should have this. It should be in there. Let's execute that, and we should have it just run successfully and know that now we print. Yes, commas always, for sure, for sure. Okay, so now that we've got our custom function loaded, now how do we call that function? Just gonna add some spaces here. So we can simply call the function by its name. So here we've named it line plot. And just like our other functions, we've got it enclosed in brackets. So when we created it, we named several arguments, which order matters. We named them axis 1, column 1, line color, and name. So these are the required arguments for our function. So for axis 1, what we've done is we've taken our data frame index. So when I go data frame.index, that provides an output, and we can copy and we can just take a quick look that looks like this. It's just a comma separated list, not a Python list, of all of the dates that are in our data frame index, or df.index. Okay. Then for our column 1 argument, we've got our df extent with our space in front, which looks something like this. It has our index and it has our extent values. Got our line color. I've chosen steel blue. You have the color list from last week, week before last, that you can pick any color you like, and then a name argument just as a title to name our plot. So now that we've got all those arguments in there, we've got them set, let's take a look at our plot. So we've got our title up top, we've got our y-axes unlabeled as we set them in our bare bones plot here, and we can see that we have our oscillating extent data for each year. We've got our plotly hover text, which is always fun to play with. And we may or may not have spoken about this before, but it is plotly, just like any of the plotly plots we use. You have the ability to click and drag and zoom, double click to return to the maximum. You can also spread the axes out. So I do encourage you to play with your plotly plots some days, just because it gives you the ability to see your data in different ways. Okay, so that should be a recap of where we managed to get to last week. Any questions on that summary?
I had to leave halfway through lab last week, and recording I think was just uploaded before this lab started, so I didn't get a chance to catch up before. I think I have most of the code in now, just from following along right now. I'm getting an error message on the first.
On this part here?
Yeah.
Okay, it's a good time for a quick pause here. Let anybody else catch up as well. Sure, Jamie, let's do a quick screen share. Let's look for some commas and other things that may be out of place and get you caught up.
Thank you.
You're welcome.
Okay. This is what I have.
All right. Bonus points for anybody who catches the syntax, if it is syntax. So, looks like I win the bonus points. Have you checked your directory? Is your directory for the location of your files the same as mine? Because currently you've got it labeled the same as mine. So
It is not going to be the same as yours, probably.
right. So where are your files relative to this notebook you're working in?
That's a great question. Right here, I think. No.
I don't think I can see anything other than your notebook.
Okay.
So best place to look is if you go into your other browser tab that shows you the Jupyter, like how you open.
Mhm.
Yeah, that one there. So where are your files relative to your notebook?
Here.
Correct. Okay, so now if we go back to the code, now we know where they are. Do you remember what that glob.glob, what needs to be changed? And the glob.glob inside your read CSV?
Um,
Do you remember what that is? Bonus points
No,
up for anybody.
I think I left like just before we got into the good stuff last week.
Okay, so right now it's a directory path or a file path. And the asterisk means all the files that end in CSV at the end of a given path. And the path currently says the folder CIS_extent. You don't have that folder. So if we,
Oh yeah, I remember this. I think you can take it out, right, and just do star.csv, and then all files that end in CSV. Sorry to
right,
interrupt. I got excited.
no, that's good. You're right, Emily. So here, Jamie, no, go back to the code. Try to run that and see if it gives you, see if it works. It doesn't work. And it's because Emily's correct that this is actually a file path that's relative to where your notebook is. So if you just remove the lab3 data / and so what this is going to do now is it's going to look in the same folder as the notebook and for every CSV file that's in there, and it's going to glob those together. So it's a relative path. It's not what's called an absolute path.
Mm-hmm.
So it has to be either just direct like this because it's in the same directory,
Mm-hmm.
or if you're looking in a different directory, you need to specify that like I did with CIS_extent.
Okay.
Relative to where the workbook is. It's a little tricky. It's kind of going back to week 1 where we talked about directories. But there you go. That should get you. So that won't work because I just put axes 1, column 1, line color. That's just text. That's not code. That was my talking point. Yeah, you got it. Nice. There we go.
Thank
Excellent.
you so much.
So Emily, that might answer your question as well. Do you still have my line of text there that said axes 1?
Sorry, I just lose Zoom. Yeah, I got it now. Thanks.
Okay, perfect. All right. Anybody else need any other help to get us squared away from last week? Excellent. Okay. So let me tee up our next step here. Okay. There we go. All right. So what you're going to need is a new cell, and there's going to be a little bit of typing. So get yourself set up and try to follow along as best you can. I'll leave it up on the screen and we'll step through each line and what it's doing. And we should be able to stay together. So, all right, I'm going to clear this and then I'm going to share my screen. Okay. Here we go. All right, so back up in our notebook. This is my cell immediately before. It's the line plot. I've just cleared the plot, but it's there just the same. And I want to be clear here that I have one cell here that loads all my libraries and my data. Second cell that just calls my columns just for visual reference. Third cell, that is my function. Fourth cell was us just taking a look at that plot. And immediately below that is this cell. Why I'm being so adamant about that is because you have to be careful which variables you've got set, which data frame you're working with, and all of that. So let's try to keep ourselves in line on which cells we're executing in which order. So here we go. I'm going to flip these, so my apologies for anybody who's started trying to write those out fast, but I promise I will. Try not to move things around too much. So I am going to pull this back up. Okay. So we are going to declare two variables right at the top here. We're going to declare an X and a Y. This time I have created this as a capital X and a capital Y. So recall that Python is case sensitive. So ensure that you are getting these as uppercase and not lowercase letters. So we've got two new variables here. The first one is going to be our X variable, okay? We're going to use a function we haven't looked at before that uses arrays. And this was the Achilles heel yesterday in our difficulties, was working with arrays. They're not always so intuitive. For any of you who may have done any matrix algebra or matrix math, that is where arrays come from. So if you love that world, you will love arrays. So we're going to call numpy, as we assigned np above. We're going to use the function array, and inside those brackets, we are going to use our df.index, which we've seen before. And this time we're going to go df.index.year. So we're only interested in the year value from our index. So anytime you see anything like this, feel free to copy that and paste it into another cell if you want to see what it looks like. So the df.index year looks like this. It's a list, or just a comma separated years, okay, as they come through in the data. All right, so I'm going to remove that because that was just looking. And following that numpy.array, we're going to use another function we haven't seen before named reshape, all lowercase. And inside those brackets, we have a -1, 1. So as I kind of mentioned, arrays are the matrix equivalent in Python, and reshaping it is to do with one-dimensional, two-dimensional, etc. I'm not going to go into that right now, other than part of our linear regression inputs need to look like this. So we reshape it. Again, if you ever want to see what you're doing here, when you've got a bigger block of code, it's harder to run one line. But you can copy it out and go, well, Adam, what does that look like? And you can execute that. And you can see how it looks a little different than when we just looked at the df.index year itself. Now it looks like it's in a different shape and it's named as an array. So you can see what that has done. Okay, I'll flip back to the top. All right, Owen, what kind of error have you got? Have you tried to run the whole thing yet? Because we're not there.
I think it's just from the previous line, the x-axis. I thought I fixed it, but I didn't run it. So I'm still getting the name of x-axis from the previous line of code is not defined.
You can't have the text in there. So your block should look like this. Do you know what I mean?
Yes, I do. One sec.
Control Z.
Okay, we're good. I have the plot now.
Yeah, if it looks like this, you don't want that. Comment
Right.
it out. That was in my notes to
Roger
walk you
that.
through the arguments.
Okay. Yeah, the plot's showing up. Okay, thank you.
Awesome. You're welcome. No worries. Okay, so leaving that plot behind, here we go. We've got our x reshaped. So moving on to our y variable here, similar to above, we are going to take our extent column out of our data frame. Again, we're familiar with the syntax. And then we're going to use a dot values. We have used this before. You may not be so familiar with it. Again, feel free to just try this little bit of code to see what it looks like. It looks very similar to what we did with the index.year. It looks like there's just all of the extent, all separated by commas. Okay? Okay. So we don't need that. Back up here, we've got our x and our y, and again, just like above, we're going to reshape the y as well. The next couple of lines here are to do with our linear regression and pulling out of our sklearn library that we loaded above in the very first cell. So we are going to name a new variable. This variable we are going to name linear_regressor. And we're going to put an equals to, good call, Nicole, we'll get there, I promise. Nicole's asking about our data values. We will get to it. Good comment. Okay, so we are going to assign the variable linear regressor to this here. And this is linear regression typeface, which means capital L and capital R, and open close brackets. So I'm not going to go into too much detail here, but this is actually calling a class. So inside this class, there are multiple functions. So by assigning a variable, in this case, linear regressor, to equal the full class of linear regression, it allows us to use the variable that we've assigned to call the functions inside that class. Don't expect you to understand all of that. You don't need to know the ins and outs of it, but I wanted to cover off what they're doing because they are important. So linear regression is our set of functions that we want to use. The next line, we use our variable and call the function fit. Inside fit, we're going to put the x and y variables that we assigned above. Okay, so that gets our linear regression piece. Similar to the fit that we used for our normal distributions in our Sky Perfect. I was just trying to hold off because I was hoping the recording.
Oh, great. Sorry, guys.
No worries. Okay, so that's gotten us here to all our linear regression pieces. Now we want to see what our plot looks like. Here, we're not going to be using Plotly, if you notice the syntax being slightly different here. We've got PLT, which leverages the pandas module and or the matplotlib. Now we may, I don't believe above that we didn't load matplotlib, so let's see if pandas takes over for me. And we're just using something we're familiar with. Here our scatter plot. We've got our X and our Y in our scatter plot. We've got another plot that we're going to overlay that's got our X and our Y predicted as we set up here. We've defined a color, and then we're going to show it. So this plot stuff should be fairly familiar to you. The syntax looks a little different, but it should leverage matplotlib. So let's give that a try together and see what happens. Oh no, we have an error. So what's going on here? I think Emily has already brought this up in the chat and shared with everybody. So we've got this NaN issue. What's going on there? A couple of you kind of mentioned it. Why do we have that? Why is it not working? Any thoughts, ideas?
You would have to get rid of the NaN values like we did the -9999s. I'm not sure if you would add it in the function that we're doing now or go back and add it to the one we put the NA values equals 99991 into. Like, I don't know which cell you would apply it to.
Right. So did the NaN values exist before we put that exception in our CSV?
Not in the extent, but maybe in years.
So we have actually created those NaNs. So we saw that there was these bunch of 999s, and we didn't want these values because they were just throwing our plots out and throwing us, all over the place. So we created NA values instead, right? We replaced the -999s with NAs. And now we've gone a little bit further in our code, and the code is telling us, nope, sorry, can't use those NaNs. So great, we're going to have to do something to revert it. But if we go back up and change our NaNs to the 999s, is that going to help us? We had a motivation for putting this here. So we need to now try to find another way to handle these. So luckily, we have seen one of these before, and we're going to use it again. But we're going to use our drop NA argument. So right here, I'm going to add a new cell directly above this one that we've just been working on, creating together with our reshapes. And in the one above here, I'm going to throw in a redefinition of our DF, of our full data frame that we've got from above. And I'm going to say, I want the whole data frame, but I want all of the NAs dropped. I don't want them. Get rid of those records. They don't help me. They're messing up my script. Okay. So DF equals DF dot drop NA with our open closed brackets. So now let's give that a try and see if we can drop the NAs out of our data frame and then try executing our plot script again. Okay, so now it's giving me name plot is not defined. So I suspected it may do that. But that's a quick fix because we know that I didn't add the library. And I think there. So we need to, for this particular bit of code, add a library. And forgive me, I didn't add it to our original cell above because I wasn't going to do it this way originally. Anywho, the error message is telling us that PLT is not defined. Okay, this is similar to it saying that name PD is not defined if we hadn't inserted pandas or imported pandas and we're trying to use a pandas function like read CSV. So to overcome this, what we're going to do is we're going to import matplotlib.pyplot, and we're going to import that as PLT to get us past that error message. Now, it should run once you've done that, and it'll give us a plot that looks something like that. Now, I'm going to give people just a few minutes here to get that to load. I'm hoping that most people had it all typed out, but they hadn't got the import matplotlib line in at the top. Let me know anyone that has an error message thrown with the import matplotlib not working, or if anybody is not seeing the plot. There are a few things that may come up, but I'm hoping it should work just like you see on my screen.
I have an error message for df equals df dot na.
Mm-hmm.
It says function object has no attribute drop na.
Double check that you've got it spelled correctly with all lowercase and you've got the open close brackets. Does it look just like that?
Yeah.
Okay, let's do a quick screen share then, because if it is verbatim, we are probably missing something prior to it. And I will, for everybody, I'll just copy that import matplotlib because it's kind of a mouthful, and those are easy things to, harder things to type off of the screen share. So, all right, df na function object drop na. Wow. Oh. Okay. Scroll above a little bit. You're 22 in. Okay, scroll down again. In an open cell there, yeah, maybe just, yeah, ahead. Just hit df. That's not a data frame. You're on
Oh no.
So let's just clear your cache. So what I would suggest is, yeah, you can restart your kernel. Yep. And just give yourself a quick save there. It's always good to do a save when you're doing these things. On the left, you got it. Okay. And so then go back up to when we load the libraries in. Okay. Run that cell. And then, yeah, let's just keep stepping down, running the cells in order. Okay. We probably don't even need those ones, but there it goes. Okay. And then just run, okay. I don't want you to run df.plot.
Okay.
Well, it's okay. You don't have to restart. Just go back up and run them again.
Okay.
So the reason with your df plot is you just didn't include brackets. So it's a different function, which I think is messing things up for you. So don't worry about that. You can just delete that cell, and run the df one. Okay, so now it's back to being a data frame.
This one just would need those brackets?
Correct, yeah. So df.plot is doing something different and it's messing up your data frame.
Would this also need brackets?
No, that's not doing the same thing. Yeah, So now if you try the df equals df drop, that should work. There you go.
Okay, thank you so much.
You're welcome. And there you go, it plots for you. All right, perfect. Yeah, sometimes, yeah, it's a good point that you can have things like, oh, I know df.plot works, but if you forget the brackets, it's not throwing you an error, so why isn't it plotting? And this is a situation. Excellent, we're back. Okay, so that's the full data set. Does it look great that the regression lines, you know, taking everything in the whole data set, or is there something else we may want to look at that would be more appropriate? Thoughts? Okay, so knowing that we've got our CI extent, and knowing that we've got our, whatever it here, 40 years, 30 or 40 years data set, and knowing that we've got this oscillation that occurs, it'd be nice to compare the same thing across many years. So it would be a good idea if we added a cell below our drop NAs and we created a subset. Okay, so what if we decided to create a new data frame variable and made this some subset of our original data frame? Now, we've learned various different ways. Well, I guess we've learned a couple of different ways that we can do this. The one that I'm going to use here is our df.index.month. So we've seen that before. And all we need to do is if we use a double equal sign and we said, let's use the month equals 1. So created a new data frame, which is a subset of the full data frame of our CI extent. And I've narrowed that just to the first month. In this case, this is January. Okay, where it equals January. Make sure you get double equals for city view to do for Python to do the equals to. So if we run that, now we've got our new data frame. Must make sure that in our little plot that we're doing here with our matplotlib, that you change your df to your new data frame, df sub, in these two places. So in our x and our y, I'm going to make sure we call the new data frame. And let's try running that again. Okay. Now we get something that looks mathy. We've got our linear regression running through more or less the center of a scatter of data points, data values over time. And you can see that our axes now is ranging from 13 to 15.5. And it spans the full 40-year data set with only our January months and overlays a linear regression line on top. Okay. So does that seems a little more helpful okay, than just a big cluster of the full data set. So now you should be able to, using this process, change your subset to whatever you please. We could change it to May if we wanted to see what May looked like. And we would execute that cell, execute the plot cell, and there, now we see May. We don't have any values in our output. Can't really tell what the numbers are. We have our axes to be able to see our range, but we don't have much more of an output on our plot. So we're going to move beyond our matplotlib here and see if we can get some more data values. I will add, just like we have in prior weeks, we can include multiple months in here as well if we chose, using our familiar isin function, which make sure I get the right number of brackets. And we would now see that there's 3 months worth of data, and the linear regression is overlaid on that as well. And you can start to see that there's a greater span away from our linear regression line because we're comparing multiple months. Okay.
Hey, Adam.
Yeah, sure.
I'm getting an attribute error on mine.
That says which?
That says data frame object has no attribute extent, but I do have the space.
Okay. Where is this happening? Here?
Yeah, I believe so. I'll re-enter it quickly, but
did you change the data frame like I've been messing with here?
Oh, I didn't see the sequence of months. Is that gonna?
It's we were just talking about it, right? It's whatever we want to set it to. This is just an exercise. I just did equals to 1, and everything should still run, right? We're not changing our script. We're just changing the data that we're putting into it, right?
Yeah, so I have the equals 1 with the double equals, and then I have my lines of code I changed to the df sub, and it's still giving me the data frame.
Did you execute this row?
Yes.
And then you execute this one and it throws an error saying there's no extent?
Yes.
Okay, what does it look like when you, I didn't mean to do that. Can I undo that? No. That was unfortunate. Okay, let's just try it. No. All right. Oh no, I did it again. Okay, let's try this. Sorry, let me just catch up. Jupyter. Okay, that I had deleted, and this one was sub. Month equals 1. Okay, so this is where we were before I start deleting things. So try in the cell immediately below df, where you assign df sub, put in df sub, and what does it look like? Does it create this?
It creates a very long list.
Does it create a data frame like this?
Yeah.
Just like this?
Yeah, it looks slightly different. Like yours looks like shorter. Like you have ellipse in yours, whereas mine is just like the full extent from 1979 down to 2021.
That's interesting. Anyway, okay, so it does that. So if you do this, does that work?
Yes. Again, the same thing, longer list, but it gives me the extent.
Okay, great. So if you copy that and paste it here, then rerun it, does it still fail?
Yes.
All right, let's do a quick screen share. The last question I'll have before screen share is, did you replace this df with df sub?
Yes. Oh, 1 sec.
Yeah.
May have just solved it. Oh, 1 sec. Let me re-enter one line here. I might have figured it out.
No worries.
Boom, there we go. Okay. I had extent where index is in that line. That's why.
Yes.
Okay.
Don't do that.
Okay, thank you.
You're welcome. Okay, so also, David, you're helping Emily out. We're good. No, and thanks. Good. Okay. All right, wonderful. So congratulations, everybody. You have created your first linear regression plot that you now have the ability to look at any month you want, nice and easily, and get a visual. All right, so let's up the ante, okay? Because it wasn't complicated enough already. That is great. It's a great tool. Wonderful. Let's us move to something a little more, which is going to be this. Okay, now this is a bit more to copy out, so I'm not going to make you do it. I'm going to share this in the chat. So put that in one cell, and then I'm going to share this second piece and put it into the same cell just below the first piece. And you should have a single cell that looks like mine here. And I'm going to move through a little bit faster on this one because we did cover off some of this. We have our X and Y again. And I'm going to move these around so it matches what we just discussed above. Okay, we have our X and Y variable. Similar, but maybe not identical because I don't think I put it in an array, but we've indexed by our year, values reshape, extent, values reshape. Same thing here, naming changes, but again, variable, linear regression, model.fit, XY, all the same, we talked about it. We're gonna add two new rows here that we haven't seen, X range and Y range, and we're going to be plotting in Plotly. And so these two rows are going to help us define the linear regression line. So the X and Y points along the linear regression line. I'm not going to go into detail here because I don't want to. This was the biggest issue I had yesterday. The long and the short is that it's the linear regression line for the plot. Okay, we're using our predict again like we did above. I've got two additional lines of code here that use the X and Y range above to make it work with the Plotly script I have. Again, I'm not going to go into too much detail. You won't need to change any of these pieces. These will stay static to make this plot work. So you will not need to edit any of this. What I'm doing here is I'm taking the last value and the first value based off the index from the X range, and same with the Y. I have to reshape it from the output, and then I take the last value, I reshape it, and I take the first value. Don't worry about it too much. I've assigned those to the variables. These two variables of the X and Y coordinates are what I put into my second scatter plot. So if we're going back to the Plotly world, you may recognize we've got our scatter, we've got our X and Y inputs, we've got our mode here, which now we've put in as a line, and we've got some color and width, and then we've got a title. Okay, that should be pretty familiar from what we've worked on so far. The first one here, again, pretty familiar. We've got a scatter plot set up. We've got our X and Y, and we're going to be doing using our X and our Y variables like we did in the matplotlib example above, but we've had to add a little function on here to reshape it. And this has got to do with our, just on how the plotly scatter uses the values and how the outputs are being generated. But we talked about what reshape does. And then we've got our markers as our mode and our CI label. I've added an opacity here, which just means that you can see through it to a certain level. This is a value between 0 and 1. Again, don't really need to worry about that. So, not changing any of this, using our original DF, you should be able to execute it and have it produce a plot that looks like this, which is very similar to the very first plot that we generated, or rather the plot prior to this that we generated. You can see that it has a line in the same spot, it has dots in the same spot, our data values, and it's all over the place. Except now, you'll notice, being familiar, we've got our hover text back. So now we can actually see a value of all of our points, and we can even see where the linear regression starts and ends. Gives us an actual value on that line. And you've got the whole zoom in, zoom out functionality, moving your axes around, hitting the little camera that downloads it as a picture. So now everything looks nicer and, you know, more front end or user friendly. Now, just like before, let's use the second data frame we created that was just a subset of our January. And just like the former plot, all we're doing is we're changing that in our X and our Y input. We're changing that data frame just in those two places, and everything should execute just the same, which generates for the month of January this linear regression plot. Again, you've got your hover text to give you all your values on the different years and your start and end values for your January regression. Okay, so I went through that a little bit faster, but most of it is doing what we reviewed in the first one. We're just now starting to leverage Plotly to give us some more of those user functions. Questions on differences there between matplotlib and Plotly? Great. Okay, we are going to crank it up one more notch here. Okay, and this last bit here, we've got 40 minutes. This is the last bit that we are going to cover that you will need and will be drawing your conclusions from for this week's lab. So let me get myself lined up here. Yeah. I am going to narrow this. So, new cell. And what I'm going to get us to do, yeah, new cell below our last plot one. I'm going to give myself some space. Okay, so here we go. We've got our new cell started. what we're going to do is we're going to create a handful of new columns in our data frame, okay? Because we're going to start using some abilities that Plotly has, specifically in their Express catalog of tools that leverages categorical data to do some different visualizations, to color code things, to group things, and all that. So because we're dealing with time series and we're really concerned about extent changes over time, we're going to start moving some of our date time data in our data frame into some more categorical or usable in Plotly Express values. So we're going to start with a dates column, a date time column, and a year column. And you'll notice the year column that we're creating, so df year equals, so this is creating a new column in our data frame. You'll recognize that this is very similar to what we used in some of our plots above. Now we're just going to put that into a column that we can use. So df.index.year.values, right? We've seen that before above. We talked about it. Dates, we're going to create a dates column. Similar to when we said years or month, we're going to pull the date out of our data frame. And here what I've got is another function inside pandas that changes the data type to a date time data type. So these two columns, dates and date time, are more or less the same, except they have different data types attached to them. We don't need to go too much into that. Just understand that we're creating a set of new columns that we can use in our plots. In addition to date, the full date, the year, we're also going to do the same thing for month. So we're going to take our month indexed, and we're going to throw that into a new column in our data frame, month. Okay. Then here's a fun one. And I am going to share this one in the chat because there's a few extra syntax pieces. And I will reiterate, try to keep up, but if you start struggling with some syntax and all the lines here, I will also share this as a finished notebook this evening or later on tonight. So let's keep pushing. This one I'm going to name month_name. So again, I'm creating a new column in my data frame. So I'm really starting to build it out. Here, starts off similar. I've got my data frame. I'm going to be referencing my index again. But this time I'm going to use something called toSeries. So this is kind of taking it from a column in our data frame to a series. So that would just be all the values. So we can take a look and see what that looks like if we throw it into a different cell. So this is our date time index, and this is our series. Doesn't look much different, but it does have an application to the rest of this line of code that we're using. I think we've seen the toApply. Maybe that was yesterday. We're using a function here on apply, and that means we're just going to apply something, in this case, what's inside the brackets, to this series that we're calling, okay, which is the dates just down here. We're going to use a lambda function. Don't want to go into all this too much detail. You don't need to manipulate it. But what we're going to do is lambda is going to apply this little bit of code here, this function, to every one of these values in the series. And what this function is it's a string time, and it's got this character B, an uppercase B. So there are a bunch of different codes uppercase y, lowercase mm, lowercase d. They all mean different things. For example, a lowercase d means day. I believe lowercase dd means 2-digit day, or rather that would make much sense, but month, for example. M is month as a single integer, whereas mm means it's always 2. For example, the first month, instead of being a 1, is a 0, 1. Anywho, the B here, which is not what's nice about the B, is we are going to take the longhand name of the month. So this column is going to be full of, instead of 1, 2, 3s, it's going to be January, February, March, April, the string name text itself. Okay? So we are going to add one more column, and this one's going to get a little trickier. And I think what I'll do is I'm also going to paste this one into the chat. So we're following along here. We've got a set of columns, additional columns. Now we're going to add a new column named season. And I'll explain what this allows us to do in the plot once we get there. So I've copy pasted this, so you shouldn't need to into the chat, so you shouldn't need to type it all out. But as a quick recap of what it is, you've seen the df.index. But we don't need to do that anymore because we've got a month column. So I can say df month for my column above here of months is in, again, one of these values. We've used that before. And I'm using this function here called np, numpy, where. So where the month is in these values, assign or fill this column with the name winter. Else, fill it with the month name. Okay, and we run that concurrently so that we, where the month equals that in our data frame, put summer into our season column, and then likewise, I put a shoulder season in. This is 100% definable, just like we have in the last lab and prior labs. You can change this set of numbers if you feel that winter season for our plotting should only be 1, 2, 3. You can change it here as well. This is fully editable, and you should understand how our season column is being defined between winter, summer, shoulder. You could add fall if you wanted. I'd like you to understand this. We dealt with the is-ins before in the past. And when you see the plot, this should make some sense to you on if you want to change these values. Okay, so I copy paste that. I'm not going to wait for people to type it. And let's go from there. I've got a couple of other things, but here we go with this one next. Okay, I will copy and paste this into the chat. But in the cell immediately below, the one here that we created our new columns, don't forget to execute our new columns. Don't worry about all the pink text. Ugh, I may change this for the notebook I provide you. Anyway, ignore the pink text. Don't worry about it.
I didn't get pink text when I executed mine.
Okay, good. Yeah, so get that in there. Make sure you execute it. Okay, so yeah, All right, so we've got our new set of columns. Pink text or not, doesn't matter, it still works. And then you copy paste it in our little, our new scatter plot here. So notice it starts with a px dot scatter with an lowercase s, not to be mistaken with the go dot uppercase s scatter. So now we're using the Plotly Express package. We're no longer using the Go objects. In here, I'd like you to replace that df sub with df for the first time we do this. And the first entry here tells Plotly the data set in its entirety that we'll be using. In this case, we're using our full data frame. The next row, I should say as well, I've added a sort, and I want to sort our data frame by months. This really is just to help our legend. We don't need to worry about data-wise why that matters. That was just to make our legend look better. Then we have our X and our Ys. We're familiar with X and Ys in our plotting by now. We are going to use the year column that we created above for our X, and we're going to use the extent column that we have been using for everything up until now. We've got a new argument that we haven't seen before, which is named facet column, and we're going to use our newly created season column in there. You'll see what that does in a moment. And then we've got a color argument, and we're going to use our month name created column, and then we're going to call this argument trend line, part of the Plotly Express package, low s. All right. And when we execute that, it should generate something like this, which is starting to look pretty neat. We've got our own little individual plot, and I've clustered it for seasons. We've got our hover text over our dots. We can zoom in, we can zoom out, just like anything with our Plotlys. We've got a trend line that tells us information, tells us all kinds of things about it, the point at which we're hovered on the trend line, so gives us the year, all that. Thanks for everybody's comments. Gives us a bunch of information over a hover right away. Nice visual, color-coded, all in order, bang, just like that. But still a little hard to read, right? But pretty cool nonetheless. So let's talk about really making it a little more readable so we can draw some conclusions, okay? Yeah, Nicole, month, you may not have the month defined. If you don't have the month as a new column, it won't find month here. Okay, so go ahead.
I have a parser error, unknown string format dates. I don't know.
Here?
Yeah.
It might be because of that. If you take this and put it into its own cell, does it run?
1 second. Yes.
And then if you do that, does it run? Does that run to create a new dates column?
No.
Why doesn't that run? What does it say?
Wait, no, it doesn't run yet. Yes, it does. It does.
Okay, great. So then I'm assuming the error gets thrown here. So if you run this one line of code, does it run?
No.
And it throws the error again that says,
Yeah, it says, yeah, unknown string format dates.
you got everything spelled correctly? But no, I don't mean to be.
No, for sure. Yeah, I think so. Should I share my screen? Oh, wait, that's why. Oh, got it.
Okay, excellent. Nicole, did your month error get resolved?
Yeah, I fixed it.
Awesome. Okay, so what I want to do now, we've got all of this, we've got all these new columns. Great. We talked about prior in our other plots how we can subset the data. And I just said, this has got a lot going on. Yeah, it looks great, but let's do some science here, right? So I'm going to call back my df sub because I like the name of the variable. And instead of month and other things we've done before, let's try something now. We've got some power of extra categorical data that we've created in the fields above. Let's go df, our data frame season column, with a double equals winter. Let's just look at our winter months. And then having created my df sub, all we have to do for the px plot is change df to df sub. And if we run those two, we should pop up with a plot that looks like this, which is now actually giving us some visual of information that we can read. Okay, again, hover, we've got all our nice little points here, tells us what they are. We've got our trend lines. We can see it color coded by months, so we can see how it behaves with our trend lines.
Can you move up to the code just quickly?
Yes, sorry. Yeah. So all we did was change df sub from what we had. And just like we've done in the past, we've just got what's called a mask. So we've masked our df on a clause where season equals winter. So likewise, we can change the season to something else. You know, summer. Maybe we're really worried about summer because, well, that's when it's hot. Maybe we want to change our summer subset that I've got July to October. I don't know. Let's take a look. So if we run that, now we're looking at our summer. Okay. I'm going to jump onto the next part. I want to add one more level to this, but I want David to come back and ask some questions about this particular plot in a moment. Okay. So what I'm going to do is I'm going to put a new cell in. Okay, and in this new cell, I know I'm moving it a little fast, but it's important. That we get here. Okay, in this new cell, you're gonna just copy and paste exactly the same plot that we just worked on, our scatter plot, and you're gonna make one change. Instead of using the low S trend line, we're going to use the OLS trend line. Okay, so that's a straight copy paste, change low S to OLS. Okay, and then we are going to add a couple of lines of code in here. I'm going to drop that for now. And you know what? I'm going to copy paste this for you because I'm in a hurry now. Okay, so copy paste, change the trend line name, and paste this in there. All right, and then if we run that, once you get there, you're going to notice it produces exactly the same plot, except the trend line now looks more like our regression, our linear regression line that we used before. It's a straight line instead of a curved best fit trend line. And we'll talk about that a little bit more. Also, if you hover over one of those lines, you'll notice now we're starting to get some more statistical data, like how it was created and an R² for our trend line. And beyond that, if you scroll down, now it's printed a bunch of other stuff. It's printed here what's called an object table. So this is a little table, shows each of our months in the bit of script we executed. And then this little bit of code is an object. And what we did in this very last line of code that I copy paste into the chat is we asked to print this line of the object, which gives us this statistical summary results all printed out like that. So things you'll recognize, we've got our F statistic in here, we've got our R², we've got our coefficient, we've got our standard error, we've got P, T, and all these others in here, okay? This is going to be your primary results summary that you're going to be using to draw some conclusions from. So one thing I need to put into this recording to be very clear on how you actually get this results table. Okay, I'm gonna illustrate this in a separate cell here. Okay, there are several things going on here. Okay, one, we are creating a new data frame, in this case, with the px, plotly expressed function, on our figure. Remember above that plot is actually named figure. It's an object. So this creates a table. Okay, we see that table. If we run this, the table looks like that. You'll notice we already looked at that just above. Now, if we want to see that summary, we need this line of code, okay, which we used above. But the summary will only show one record from this table at a time. So you see that there's a 0 here. So everybody needs to be paying attention to this one and make a note of the time this is in the recording. This will be important. The 0 relates to the 0 up here, which means 0 equals July. So when I execute this, all of these stats are from July. If I change this to a 1, now it equals August. So when I execute it, it is now the summary statistics for location by location 1, which is August. Okay, so it's important to pay attention to the summary that you're getting is from which month, because each summary, the way that we built the plot, is summarizing the statistics from a given month. And when we're using our seasons, you need to be aware of what the summary stats are showing you. Okay, so that's where we needed to get to today. You may have fallen behind on a bit of the code because we went fast at the end there, but I will share it this evening. I did want to go back up here to the trend line Lois plot and give David a little bit of an opportunity here to talk about this plot and inferring some things from it, because we did talk about this last week, and I know this is a good talking point. So, David, are you around?
Yep.
Yeah.
Thanks, Adam.
You're welcome.
Yes. Whenever we fit these linear regression lines, an important point is that they are linear, meaning that they're a straight line. So they're trying to fit a line through the data that basically what's called minimizes the sum of squares of the distance between the line to the points. So, I mean, we don't have to get into too many of the details, but actually linear regression is a calculus minimization problem at its heart. And then the formulas that are used, like if you learn about linear regression, those are what are called an analytical solution to this minimization problem. And this is basically what all fitting problems are. You're trying to get a line or a distribution that passes as close as possible to all of the points kind of at the same time. So, and then you're stuck with whatever form you've got. So like the last lab, you know, when you were first plotting the data, you saw the bimodal distribution in the data, and yet the Gaussian tries to, you know, does its best to fit that data. So, I mean, it looks kind of silly, but I mean, the Gaussian's limited to one bump, basically. So, so in this case, we've got a straight line running through all these data, trying to be as close to all of the points as possible. Okay, so when we, where are the ones?
Here.
Okay, yeah, so, you know, so an interesting issue arises if the actual trend is not linear. And so, you know, this difference can be highlighted a little bit by doing what Adam's done, which is doing the straight line linear regression or ordinary least squares linear regression, and what's called low-S, which is it's basically like what's it stand for?
Locally weighted
Locally weighted estimator.
Smoothing, yeah,
Oh,
smoothing
okay,
line.
yeah. Thank you. So the low-S is better able to capture perhaps some of the non-linearities in the data set, or in the time series in this case. And so you can see, you know, that, okay, look at all of these ones that right around the early to mid 90s, there's almost like a bit of a break point where something changes. You know, we had a declining trend before that period, okay, and then afterwards, it looks like it gets worse, and it's not just sort of a phenomena confined to a single month, but it's kind of like across the board for these late summer, early fall months, right around sea ice minimum. So that's just always something to keep in mind. And it's something to keep in mind when linear regression is used as a predictor, which it often is. And the reason for that is we don't have an annualized rate of change, it's called. We can't apply an annual rate of change to a low-S plot, because the rate of change depends on when you're looking at the time frame. If you just plot a straight line through all the data, okay, then you've got the exact same rate of change for each year, and you can use that for prediction purposes, right? So you can ask the question, well, we go up to 2020 here. Well, if slide down, Adam. Thanks. So the data go up to 2020, but somebody might know, like a shipping company, like what's the sea ice extent going to be in 2030? Well, how are you going to predict? The best way to predict, the only real way you have to predict, is to just extend that line to 2030. Use the regression equation and make an estimate for 2030. Knowing that it's not perfect, you know, in some cases. So it's always the trick with this straight line linear regression. You know, we can find other functions that might better follow the ups and downs of the data. But with those, we don't have any way of actually making a prediction. So in a sense, a straight line linear regression is what's called the most conservative solution for a problem like this. So, yeah, and then the statistics there, you get a bunch of little stats, and they're basically giving you information about things like whether the data that have gone into it are normally distributed. So we're coming back to that. Remember, we looked a few weeks ago at how outliers can affect linear regression, and that you know, linear regression ends up tracing back to the mean. So and we remember that the mean as a statistic carries some problems with it. It's dependent on, excuse me, on being having a Gaussian distribution to the data set. Linear regression is the same. It pretty much wants the data to be, you know, more or less normally distributed, or it starts to fall apart a little bit. So some of these stats are telling you about that. You don't really need to dig into the stats to, you know, for the work and so on. But that's what some of the stats are getting at here. And then the R squared. So remember, that's the coefficient of determination, and that's a measure. Actually, who can tell me what that's a measure of? So we know what correlation is. Remember what coefficient of determination measures?
The covariance.
The covariance, that's the correlation. So correlation is covariance divided by the standard deviation of the two variables involved. Yes, how much variability in X is explained by Y. That's right. So that's what the coefficient of determination is giving us. So even though and people will sometimes use R squared as like a more rigorous version of R or something like that, but they're actually measuring two different things. And yes, they're related, of course, but they are technically quite different in as metrics, as statistical metrics. Let's see. Yeah, I think that's probably good for now. So some of the questions in the lab will center on just having a look through some of these plots, just kind of seeing what, you know, letting their message come home to you. Because like I say, these are state-of-the-art data. So we'll have a reading, maybe two. I think I want to put a little reading about using linear regression for prediction. You make a little prediction in the lab questions. And then I'm going to put on an IPCC reading, actually, that delves into, you'll look at the chapter or the section, it's not a whole chapter, it's just a section that delves into details about Arctic sea ice loss. Yeah, it's pretty interesting stuff. And you look at plots like this and say, whoa, like what happened in the 90s? It's like it kicked into another gear. And that's it. That's our world. So it was people writing in the chat. Ice cores. Oh, and that is true about the past as well. Oh, you mean like taking an annualized rate of change and running it into the past? Is that the idea?
Yeah, if we can extend the line back to the past. Would that be just as accurate?
Yes and no. There's always a problem. I mean, this raises a larger problem about making, these are called extrapolations. So an interpolation is taking a measurement from within the data set. You've got your time series and you've got a fit. Taking a measurement from within the data set, it's well constrained, it's called, because you've got data on either sides of it. So, and that's called interpolation. Once you run beyond the end of a data set in either direction, that's extrapolation, and the error bars start to really grow pretty rapidly. I mean, that's kind of another topic, but and you quickly get into, like, you can imagine if you took some of these lines and said, or if you slide down, Adam, you know, if you took the annualized rate of change and said, okay, well, I want to see September. I want to see what the sea ice concentration for September of 2100 is going to look like. Well, if you just apply the standardized or the annualized rate of change, what are you going to get? Well, you're going to get a number that's way below zero. And that no longer makes physical sense. And it's just like if you run it too far back in time, you'll get an area that's larger than the Arctic Ocean. And that also, you know, so at some point you quickly exceed the boundaries of what makes physical sense within the, you know, this particular natural system. So yes, it works to a limited basis, but often it doesn't. And I think Emily mentioned ice cores. Ice cores is a whole other discussion. Ice cores look at the far past. And ice cores, when people take ice cores, they're not taking cores of sea ice, they're taking cores of glacier ice, of terrestrial glacier ice, such as on the larger ice caps, like Greenland, but also places like Agassiz ice cap and Devon ice cap, which are smaller ice caps in the Canadian high Arctic. Even Mount Logan, they're ice caps that people take from alpine glaciated sites as well. And those were looking at broader pictures of climate changes. So yeah, no, it's ice cores is an interesting subject. I mean, with the Antarctic, we can go back almost 1 million years with ice cores. And that's how we know, actually, just to wander off on this tangent, that's how we know we have plots of what the carbon dioxide concentration in the atmosphere was like 800,000 years ago. Well, how do we know what how do we know what the atmosphere was like then? Well, we know it from these long ice cores, because as snow falls, of course, it's fluffy, you know, and it's got little air spaces between it. But as more snow falls on top, the snow that's underneath gets more and more compressed. It gradually turns into ice. But there are little bubbles in it that basically are retaining a sample of the atmosphere that existed at the time when the snow fell. And, you know, with a bit of careful work, you can extract that little tiny bit of gas and measure the relative quantities of different gases in it. It's pretty cool, actually. And there's some amazing work from, or I won't be hyperbolic, some very interesting work from, I'm looking at the books by Bill Rudiman. If people are interested in this kind of thing, I can point you in those directions. But carbon-13 versus carbon-14 as well. Oh, okay. So that's another type of dating. That's, yeah, carbon-14 dating, where you've got rare isotopes of a lot of elements that are radioactive and then have a half-life. But we're kind of running beyond our thing. Yeah, if you want to talk about that stuff, I mean, I used to work in a radiocarbon lab as well. Yeah, we can talk all about paleo stuff as well, because I've done lots in that. But we're wandering off of sea ice for the moment. So I'll give it back to Adam. And if people have other questions, I guess, fire away about the lab. Or yeah, if you want to talk about these other topics, I'm happy to talk about that stuff as well. It's all extremely interesting.
Is it next week that the next lab quiz will be due? Okay.
Yeah, yeah. Let's just call it a lab. I don't like hanging quiz onto it.
Assignment.
So I'll give you the questions, yeah, like later today. I'm just making sure the references are not too lengthy and they're sort of to the point.
Yeah, and I'll clean up my notebook here and lay it out as we run through it today. Yeah, so that's everything. We're at the end. I know that Owen has a couple of questions. He's still getting things that aren't quite working. Anybody else is welcome to stay on with some questions for a few minutes. But other than that, we're done and we can wrap up the recording.
And sorry about my computer dodged out a couple times on the internet. I ended up bringing it up. It's actually recording on it. I've got it up on another computer here. Oh, and I didn't actually turn the recording off, did I?